My name is Rolf Findeisen, and I have the pleasure to introduce Danielle Quevedo. Actually, I know Danielle probably now since 15 years, something like that. And we have also
1-5, not 5-0.
Okay, so let's get started. So Danielle doesn't need that much introduction. Actually, he studied in Chile, bachelor, master, I think that was. But then he said, let's travel a little bit the world. So he went to Australia, did his PhD in Newcastle with Graham Goodwin. There he already started working a little bit on control networks and other things. Then he decided maybe it's time to change a little bit. He actually had some time also in Germany, but then he decided to go to Queensland, I think 4 years ago. How long is this?
4.5 years ago.
4.5 years, but he will change affiliation again. He will be moving to Sydney University in September. So having said that, Danielle works on various topics, mainly on network systems, some NMPC things, something on green control, and he has also received a couple of awards. So Danielle, the floor is yours. I'm looking forward what posterior sampling means.
Excellent. Thank you, Rolf. Thanks for your kind introduction. So yes, I've moved around a lot, and it seems nobody wants to keep me for very long at one place. So next week I'll be moving to Sydney, and would like to invite you to that. Thank you, Moritz, for inviting to give a talk. That was sort of a little bit on short notice, which gave me also the advantage to have a look at which talks were on already, and which showed me then, okay, it's not purely NMPC. There's quite a bit on interest in reinforcement learning, which we've done a bit of work as well with my friends. So I can't talk about reinforcement learning. So what else can I talk about? I thought, okay, let's talk about something that a few years ago I knew nothing about. Now I know a little bit about, and I hope I can entertain you now for 1 hour. Has anybody of you heard about Thomson sampling before? A few people. So you, right? Okay, let's say maybe 2% of people. Hopefully, with today's talk, I will firstly keep you awake. And secondly, you will have some take-home message about Thomson sampling. So my talk is about posterior sampling or Thomson sampling for channel selection within network estimation and control. It's joint work with Alex Leong, my collaborator for many, many years, 10, 20 years, I don't know, and with Wan-Chun Liu, who we've been working on for 5 years approximately. So advances in wireless communications, embedded processors, and sensor technology. Shall I get this closer? All right. How about this? Okay. Can you hear me better now? Yeah. Thanks, Rolf. I will not talk the whole nonsense again that I said before. Welcome. Stay awake. So advances in wireless communications, embedded processors, and sensor technology have really changed the world we live in. Right? We can now control systems before we were not able to control before. Because wireless systems can be easier to set up, easier to maintain. I mean, we work with wireless systems all the time and continue to evolve, right? We can think of applications to autonomous driving or coordination of driving, etc. However, wireless communications are always unreliable, and this raises significant challenges if we want to do closed-loop control. We've got fading and interference between users, for example, and wireless communications then introduces data dropouts and delays. And these are actually really difficult to model in practice. And overall, then, the co-design of control and communication is rather difficult. And a whole lot of people have been working on this, including ourselves as well. So there are other entire workshops dedicated to networks and control, right? And the challenge is, if you want to design network control systems, are actually really related mostly to the fact that digital communication links introduce random data dropouts. So if we've got a control loop and there's data dropouts, it means that intermittently we are running things in open loop. And there's not really much you can do about this. You can be clever and try to predict things. If you're really lucky, you do that well. But overall, it is open loop every now and then. Because communication resources are limited. An open loop is really a big problem. It raises stability issues and performance issues. And another problem that arises is the communication resources are not only limited, they're also quite difficult to model. They're especially difficult to model if we're thinking of things like communicating between cars or communicating on a factory floor where there's metal robots, let's say, moving around. It turns out that then that the network is itself a dynamical system, a stochastic dynamical system that we need to take into account in the design. If, for example, we think about using NMPC for wireless control, for control over networks, like in that picture on top there, yes, we can do very interesting things. And I guess due to that picture is that I'm standing here because I've worked in model predictive control for network systems for a while. And we can trade computation for communications, for example, by using online computations in NMPC and communicate every now and then, use buffering and actuators, etc. Ideas that probably many of you are familiar with and that we will get back to in roughly half an hour. Another thing is that modern technology, modern communication technology also introduces additional freedom in the design. A channel is not just a channel in communications. You can choose different frequency bands, a little bit like if at home we've got 2.4 gigahertz, 5 gigahertz, we can pick those. We can use different modulation schemes. And all of these could be also done on the fly. So we can select communication channels, and that's something I will build on today. So in this talk then, we're interested in remote estimation and control of a dynamical system. The communication is wireless and poorly modeled. So I will not assume that we exactly know how good the communication channel is. And that's a big challenge, at least for me it was a big challenge to understand a bit what's going on. We will exploit the fact that often more than one communication channel is available for communications. And what we want to do then is to learn which one's the best channel. Because if we can pick channels, we would like to pick the best. We don't know how good they are in a priori, so we need to learn the quality of the channels, but we want to learn this on the fly and very quickly. Because if we don't do things quickly in control, well, things blow up. Let's say the plane falls off the sky, or we have, in general, stability issues, performance issues. So we will cast this as a multi-armed bandit problem and use posterior or Thompson sampling methods to solve that class of problems. In outline then, I will start with talking about remote state estimation, just to set the ideas and go a little bit into details. And I apologize, it will be a little bit technical, hopefully not too much for a jet-lagged audience. I'll talk about posterior sampling for channel selection. One of the nice things of using posterior sampling and Thompson sampling is that we can prove things. We can prove things in relation to stability of the system, performance of the system. And we are control theorists. We love to prove things, right? I will then apply the ideas towards or hint at what to do for networked closed-loop control and summarize and present a little bit of an outlook of what could come next. This is sort of preliminary work, so there's a lot to do if anybody's interested. So, what do we mean with remote state estimation with multiple channels? Do we? No, we don't. Okay, and wasn't organized enough. We've got this. So we've got a physical system, let's say a linear time invariant system, Gauss-Markov system, right, with sensors that would like to communicate over unknown communication channels to a remote estimator. The remote estimator uses the information it gets in order to obtain an estimate of the state. Nothing new, things that we know from our very preliminary control courses. The special thing here is that transmission is over a wireless network, and therefore, thank you, Rolf, affected by random dropouts. And different communication channels are available for transmission. So our challenge is then that the state estimates obtained by the estimator, let's say x hat of k, should be good, even though we have dropouts. And our key idea here is then to use channel selection to minimize the covariance of the estimation error. This is all stochastic, so good here we interpret as covariance of the estimation error. So what does the sensor do? Well, under observability, controllability assumptions, we all know that the sensor would be capable of using a local Kalman filter to compute the conditional mean. Let's say we call this x hat ks, s like sensor. And that's what the sensor does locally and would like to transmit to the remote estimator. We can quantify then the quality of that estimate through the estimation error covariance at the sensor, which is again this second moment conditioned on all the available data. And we will assume that the sensor Kalman filter has reached steady state. So this has been running for a while, and the quality at the sensor, the quality of the estimates at the sensor can be characterized by this P bar, or overline P. So the sensor wishes to transmit its local estimates to the remote estimator. However, trouble is, sensor transmissions are affected by dropouts. So which of the M channels should be used? Some channels are better than others, but we don't know in advance which one's the best channel. So we've got wireless communication, and we will still model the communication channel somehow. We model the communication channel by introducing a binary random process, let's say gamma of k, wherein gamma of k is equal to 1 if the data is successfully received at the estimator at a certain instant, and 0 otherwise. So 1's good, 0 is bad, and this switches all the time. We will assume that the M channels are mutually independent in IRD with success probabilities and given by theta m, which is in the probability of success given that a certain channel is chosen, and we've got m of those. So these theta m actually, these are really important for this talk, so remember this, yeah? So these are the channel parameters that are difficult to obtain in practice. They are related to fading, multi-user interference, etc. And we will assume that theta m are not known for this presentation. What we want to do is learn the channels and then pick the best one, and do it quickly. So the remote estimator will then try to do its best, which means whenever data arrives from the sensor, it overrides or it synchronizes its current estimate with that received, and if no data arrives, well, it just propagates through the model. It's the best it can do. And we can also, this is quite simple equations, right? We can characterize the state estimation error covariance, which then follows a recursion wherein the estimation error covariance at the receiver is equal to the one at the sensor at every instant when the data arrives, or grows, let's say, quadratically whenever data is lost. So I'm sure some of you have seen this sort of equations before. This is quite classical if we talk about control over networks or estimation over networks, and lots of things are known about this. Firstly, if A is an unstable matrix, so with eigenvalues outside the unit circle, this may grow. So if you've got lots of dropouts, this grows a lot, intuitively. And what we then also know is that if one always uses the same channel, then there exists a minimum success probability that that channel has to possess in order to avoid the estimation error covariance to blow up. This success probability, let's say critical success probability, is given by 1 divided by 1 minus 1 divided by spectral radius of the matrix A squared. And this is a necessary and sufficient condition for the expected value of the estimation error covariance at the receiver to be bounded. So this is very well known if we do transmission only over a single channel. What we want to do here, though, is pick channels. Learn channels and pick channels, and do that quickly. So a standing assumption is, of course, then for us, that at least one of those channels that we pick has to be good enough. So it has to have a success probability not smaller, or let's say strictly larger than that critical one. We don't know which channel that is, but this is something we require. So what do we do mean by channel selection then? Well, what we're saying here is that at the beginning of each time slot, the selector, channel selector, which is at the receiver, decides over which of the M channels the sensor should transmit its current estimate. So it chooses a decision variable, let's say mk, which is between 1 and capital M, wherein mk is equal to M, if and only if the sensor uses that channel M. Once the decision is taken, then the selector informs the sensor and the sensor transmits over a wireless channel. So the key issue then is, how do we quickly select this best channel given the channel qualities are unknown? How do we learn these? Okay, so this is the problem then, right? We want to find the best channel from dropout information. So all we can learn from the communications is whether data has been successfully received or not. So we've got information, dropout information, quality gamma of k. And this during runtime is a specific multi-armed bandit problem. Now what's a multi-armed bandit problem? Well, I'm giving you the hint here, right? This is bandit slots, a little bit like pachinko, but not really like pachinko, right? So it comes from, well, yes, I live in Brisbane. We have a lot of those in Brisbane. And you stand it comes from standing in front of those machines. Each of these machines has got a certain probability of giving you money, and we want to become millionaires. So we stand in one of the machines, we see how the machine is performing in our little brains, we try to estimate if this is a good machine or not so good machine, and we keep on switching machines, right? Until we find hopefully the best machine and earn a lot of money, right? So it's a gambling problem. It's got M slot machines that are then called bandits. I think in the US they're called bandits. Each bandit has an unknown reward distribution, and the player tries to maximize its cumulative reward based on trialing and observing. So the player conceives a sequential selection strategy for the machines. And given this motivation, you wouldn't be surprised that there has been a lot of work in this class of problems. So multi-armed bandit problems then arise a special model within reinforcement learning, so they're used within reinforcement learning, and also arise in general in the sequential design of experiments, so in experiment design, an area that some of us may be more familiar with. So decision making then needs us to consider exploration versus exploitation trade-off. What do we mean with explore? Well, we'll keep on trying different machines or different channels in order to acquire new knowledge, to learn more about the world. But every time we explore, we may be missing out on exploiting that knowledge. So we need to trade one for the other. Exploiting then is to optimize our decisions based on the existing knowledge. So this is very typical in general learning problems, right? The special issue here, though, is that the learning or the bandit problem is coupled with a dynamical system, right? We're not just learning the best channel, but by choosing the channel, we're also interfering with the remote state estimation. And the quality of the remote state estimation, well, is governed by this stochastic recursion, which can blow up, as we all know. So this then raises additional challenges on stability and performance. And that's then what motivates or has motivated us to then study what happens if you use multi-armed bandit algorithms for this class of problems. So how do we model all of this? In order to understand what's going on, yes, we can run simulation and say, see, it works really well, and it does, by the way. I was so surprised. This is so cool. It works really well. These methods are very, very powerful. But we want to also understand a bit more what's going on. So we start with modeling this, and we will adopt a Bayesian approach where we regard the success probability, so the channel parameters, as random variables that we want to learn over time. So the probability density functions of these parameters, so the parameters have got a probability density function, and these probability density functions then reflect our current belief in the channel qualities. And as we observe events, so success or non-success of communications, our beliefs change. We learn more. And that's then reflected in those distributions. So we learn from the environment by updating the posterior distributions. We start with an initial guess of the distributions of all M channels. We observe a first dropout or non-dropout, which then gives us a new distribution at the next instant, which is then the conditional distribution conditioned upon the dropout. And we do that successfully, so one after the other, and keep on refining our knowledge, our belief in the channel qualities through how these distributions evolve over time. And this may sound complicated, but for this particular problem, it's incredibly easy to do. So bear with me with just some simple integrals, yeah? So suppose that at time 0, we have no information about, let's think of one channel, right? We've got no information about that channel, so we start with a prior distribution which is flat, right? It's a uniform distribution between 0 and 1, we know nothing, right? Then we transmit over a channel, and suppose, oops, which one? Here. This is successful. So we can use Bayes' theorem to update our belief, right? And we can use Bayes' formula that says that the posterior distribution, once we have observed the channel outcome, is given by the prior distribution, the one we had in the beginning, multiplied by the likelihood of that success, given the theta, right? Divided by a normalizing factor, which is on the total probability of success. We can do the calculations, right? Theta integral here, and we obtain that the posterior distribution is 2 times theta, which is this curve we've got here. So we started with a uniform, we observe once, and we get this new belief. We have learned that the channel is probably better than just completely uniformly distributed between 0 and 1. So we can also, if we wish, we could take the expected value of this and represent the channel by a probability of 2/3. But we can do better than that because we actually have this whole distribution. Suppose that at other instances later, transmissions are not successful. We can still do our computations, and we can see that the probability, for example, the posterior to be used at time 2 is given by this expression here, polynomial, right? So we have moved from initially the blue curve to learning the red, and then we learn the yellow one. The expected value is still 1/2, but we've learned a lot from the blue to the red because we've got a new distribution. And if this goes on and on and on, we keep on learning and we keep on adopting distributions to reflect our belief. So over time, then our belief about theta evolves, distributions become more concentrated, and we should become more confident about assertions and decisions to be made. But to do that, we probably need to use the entire distribution, not just a point estimate. So there's a problem with this laptop, by the way. It says low battery. Is this plugged in? Okay, you saw. Okay. Okay, so we saw that these computations, at the end of the day, what we had is theta and y minus theta, where the theta. Oh, all right. Where the theta was related to successful transmissions, 1 minus theta related to the dropouts. So this can be done in general, right? And we arrive at beta distributions. So if we take the uniform distribution as a prior for all M channels, that it turns out that if we transmit n times over a certain channel and there are Sn successes, then the posterior for theta can be calculated in the same way, and is just given by a beta distribution with certain parameters alpha and beta. So the probability of theta, of the quality of the channel, given n transmission and Sn successes, is given by these two polynomials and a normalizing factor in front of it. So this is now a closed form expression, which is really pretty, because it allows us to do things quite easily for this particular problem instance. So direct calculations, we've got as a mean is alpha divided by alpha plus beta. So that was our point estimate we had before. And the variance is alpha beta divided by alpha plus beta squared, alpha plus beta plus 1. So as alpha and beta grow, the variance decreases and the whole distribution becomes more concentrated. So if at channel k, at time k, the channel M is chosen, then the updated parameters are simply given by adding to alpha the success, or to beta adding if there's no success. So the computations are incredibly quick, and this can be done very easily. Now, how do we do the decision making then? We've got these situations of learning, and if we look into this, by looking at this curve, would you make a very informed decision of which channel the best channel is? Well, I'm not really sure. I would probably say, let's explore a bit further. And if we explore further, we'll arrive in this type of situation, where then we could say, aha, yes, the red channel is probably the best, right? So we have this exploration versus exploitation trade-off, but we can quantify it quite well by using these distributions. So how do we then allocate our exploration efforts? Well, don't know. Let's have a look at two easy to implement and well-known classes of bandit algorithms. We will look into epsilon greedy algorithms that I'm sure some of you have heard upon, and we will talk about Thompson sampling. So what's epsilon greedy? Well, as the word says, there's a part which is greedy and a part which is random, right? So epsilon greedy channel selection is quite simple. With a certain probability, let's say 1 minus epsilon, we choose the apparently best channel, so we exploit. And with the other probability, epsilon, which has to be larger than 0, we choose a channel uniformly at random. We explore. So we keep on exploring, right, with a certain probability epsilon. So we start by setting all channels to be, let's say, uniform in principle. We pick alpha divided by alpha plus beta as the expected value. The channels are represented by those expected values. And we then pick the channel either as by drawing uniformly or by picking the best channel out of those expected values. We choose a channel, we transmit, we observe gamma, and update our distribution parameters for that channel that we used. So it's a very basic algorithm. It's general purpose. It switches between exploration and exploitation in a random manner, in an independent random manner. This epsilon is called exploration rate. It may be time varying, and people that work on this know in general you will pick it time varying. And it's a key tuning parameter. And like so many things in machine learning, it's one of these tuning parameters where how to tune them is a bit of an craft, an art form. It is very difficult to get precise results on what to do, right? The method is used in basic model-free Q-learning, in Q-learning with tables, for example. Oops. And then another method is to use Thompson sampling, using the entire posterior. And that's a really nice one. Look, it goes back, it doesn't go back to actually sitting in a casino in front of machine. It actually comes to trying drugs on people, right? To make a choice between what type of medicine to use in a population in order to increase the probabilities, or let's say, the likelihood of the people recovering. And you'll understand this is something that you want to do quickly. You don't want to use a lot of experiments in order to finally find out what to do. So in 1933, then Thompson came up with this idea, and hence the name Thompson sampling, of not just using the mean values, because if you look at these two pictures, the mean values remain the same, but work on the actual belief and really use the belief that we have in order to make the decision. And the channel for us in channel selection, the key idea is actually really simple. Look, we've got these distributions of the channels. If we want to make a decision, let's just take a random realization from those distributions. So we replace the channels with a random sample from their distribution, and then we pick the best channel. And that's it. Very easy, quick to do if you can sample quickly from a distribution. So the method then, as before, we initialize, we can start, let's say, from uniform. Then the special thing is that we sample from the beta distribution and then pick the best representation or the best sample, which is then associated to a channel, transmit over the channel, update our distributions, etc. So again, this is a general purpose algorithm. It's application agnostic. It's a randomized policy because the algorithm itself takes random samples, right? It's a randomized policy and explores randomly depending on the difference between the random sample and the expected value. Over time, since we're learning, the variance of the distributions decreases, the distributions become more concentrated. Over time then, the Thompson samples will become closer, will more likely to be close to the expected value. So over time, we stop exploring slowly. So this algorithm will typically tend to explore less over time. But we don't need to tune anything. There is no exploration rate that magically we need to tune somehow. This just works by itself, which is really nice. So, this is then how it works, right? We've got our Thompson sampling algorithm, and we keep on sampling from distributions. It continues to choose all actions that could plausibly be optimal, because it keeps on using the entire distribution, then just picks every time the best one. You will notice, for example, this is using Thompson sampling, right? You will notice that over time, this is after 922 time steps, we are learning more these two good channels, less of the bad channel. Well, because that channel is quite unlikely to be optimal. So it gets chosen less often automatically. And the exploration efforts are more focused on discriminating between those two. So, posterior sampling has been studied a lot and is currently being studied a lot in more general reinforcement learning as well, also in control where data efficiency is important. So we don't want to do offline using a lot of data for a long time to train our neural networks. We want to actually do things quickly. Quickly because we're talking about control, quickly because data is expensive, quickly because data also uses energy. So the main idea then is that we've got model parameters, which could be transition probabilities, rewards, costs, that are described by probability distributions. At the beginning of each instant or time step here, or we can talk about episodes or a dynamic episode if you wish, a single model is chosen, and the parameters are then sampled and assumed to be correct. We compute actions. For example, what we did here is pick the best channel, or you can do NMPC, or you can do LQR, or anything else you wish. The actions are implemented, we observe from the system, and when we update the probability distributions of the parameters, and we go back to step one. And this you can do a lot. But then what happens if you do this for a remote state estimation problem? What happens with stability and performance? We talked about the estimation error covariance, which quantifies the quality of the state estimates. And it's a possibly diverging random process governed by this switching stochastic process. It raises stability and performance issues. So about stability, let's talk about boundedness of the error covariance process when we're doing learning and channel selection in real time. So what we need to do is investigate jointly the learning dynamics, so what's the probability of picking the right channel? How does this progress over time? And the process dynamics itself, which here I'm writing down as the drift of the estimation error covariance next instant given the current, which incorporates the quality of the channel, so the success probability of the channel chosen by the learning. So our results that I'll present in 20 seconds merely require that one channel is good enough, so we don't know which one, but one has to be good enough. During learning, some of the optimal channels, of the suboptimal channels, may be used too often so that the expected estimation error covariance may diverge. But luckily, that's not necessarily the case. So if we use the epsilon greedy algorithm with a fixed exploration rate, then we can say that the estimation error covariance in expectation is bounded for all times if and only if the exploration rate is not too high. And here's an expression for that. I will not go into the technical details, they are in one of the papers. For Thompson sampling, the assertion is more difficult to prove, but it's very, very quick to state. So with Thompson sampling, the estimation error covariance, so expected value of the estimation error covariance, is always bounded, and that's it. There's nothing to tune, and it just works. And I thought that's really fantastic, because we've got an algorithm that's to implement is just a couple of lines. The analysis may be complicated, but at the end, this works incredibly well, and provably well. So that's stability. What about performance? How do we quantify performance here? So performance, we will adopt the notion of regret, which is used a lot in the machine learning community. This is where we got it from. So we will quantify the degree of suboptimality, so how far away is an algorithm from an optimal algorithm, by means of a cumulative measure. So an added up measure from time, let's say 1 up to current time t, which is then the cumulative estimation regret over a certain horizon t. This is how we define it then. As cumulative regret up to a horizon or over a horizon t as a difference between the expected value of the estimation error covariance with a particular algorithm minus the expected value of the estimation error covariance of the optimal algorithm. What would happen if we just always use the best channel, that we don't know which one it is? And it turns out that if we use the epsilon greedy algorithm and the exploration rate is such that we have stability as defined before, then the cumulative regret scales linearly. That means that there exists constant C1 and C2 in a certain time instant from which on the regret is upper and lower bounded by linear functions of time. Perhaps not surprising for those of you that work in this style of algorithms, but what is new here is that we're actually not looking at the algorithm itself, but how it influences estimation error covariance, which in itself could be a diverging process. Similarly, for Thompson sampling, the analysis, yes, it is more tricky. However, we can also prove then that the cumulative estimation regret scales logarithmically. So it scales much nicer. It grows slower than linear, as written in this result. So let's alleviate a bit and let's have a look at a small numerical example where we've got 4 channels, system, just a simple system, artificial system, and we've got 4 channels to choose from, each with its own channel success probability, let's say 80%, 70%, 60%, 50%, unknown. And what we want to do is learn, choose channels, remote estimation, everything at the same time. And this is how it goes. This is a single simulation run. We say in the upper plot, we've got the channel choice over time, up to 1,000. In the lower plot, we've got the posterior mean, so the alpha divided by alpha plus beta over time in our belief of the channels. All of them started roughly 1/2, which is we don't know anything about the channels. We see that the Thompson sampling will be trying different channels for a while, and then after a while realizing that the best channel is the blue one, the 80% one, and devote most of its exploration efforts to learning that channel a bit closer, discriminating it, and over time it will stop exploring, not completely, but reduce exploration of other channels and focus on the best channel. So this works quite well. The estimation regret averaged over a lot of simulations. We can see that the estimation regret scales linearly for the epsilon greedy and logarithmically for the Thompson sampling. So it outperforms by far. Let's get back to control. Let's try to talk a little bit about network control systems, because at the end of the day, we don't just want to do remote state estimation. We want to act on systems. We want to influence the world, right? So suppose we've got such a setup. We've got a control algorithm that through a downlink, M unknown channel goes down to the physical system. The physical system has got sensors, like we had before sensors. Uplink goes to the state estimator, which then allows us to do controls. We separate estimation and control like doing in most of what we call modern control. We will assume here that we've got a time division duplex communication setup where you can either transmit from the controller to the actuator or from the sensors to the estimator, but not both at the same time. So we either can use the uplink or the downlink, but not both links simultaneously. And these links, though, could use any of the M available channels at each time slot, like we had before. So in addition then to channel selection that we talked about before, the control algorithm then schedules the uplink and downlink transmissions. Let's say we have another variable, let's call it nu of k, which can be either U, like uplink, or D, like downlink. The decisions are then communicated to sensor and actuator via an error-free transmission management channel. So that's an assumption we have here, that those control, or let's say transmission management channels, are error-free. For the scheduling then, for the deciding whether uplink or downlink transmits, we will not do that in an optimal manner. We will just use something called persistence scheduling, where the sensor node is scheduled to transmit until it's successful, right? So it transmits until successful, and then the controller transmits until successful, and we move from one to the other. All of this is obviously random because we have random communications. So this is our setup then. Okay. So the controller then uses the optimal estimates that we had before, same as the ones we had before, just with an input now, but the controller decides the input. We've got acknowledgements, so we know the input. We're not doing estimation with unknown inputs, yeah? And adopts a linear control law for generating a control signal once it's scheduled. So let's say we've got K designed, and that's a linear control law. The actuator then adopts a hold input strategy, which applies the most recently received control signal as an input. So the input to the system is either what the controller designed, right, if the data has been received at that instant, or otherwise it's just kept constant. A fairly simple setup here. And then it turns out that we can, using some related techniques, we can establish necessary and sufficient conditions for mean square stability of the control system, which then depend on properties of this random matrix that we've got here. Yeah, that's mean square stability. I will not go into details. And we can also talk about the control regret using posterior sampling. And again, it turns out that if we have stability as mentioned before, then the control regret scales logarithmically. So we've got guaranteed performance in a stochastic sense. So how do we apply all of this now to model predictive control? I somehow need to justify why I'm talking to this audience. So people have been working on model predictive control for network systems for a while, and ourselves also have been doing things for a while. So the standard thing, relatively standard thing, whenever we have wireless communications, is that the controller not just transmits a single action to be implemented, but it transmits, let's say, the entire optimizing sequence, because we've got it anyway from our open loop model predictive control optimization. That data is transmitted to an actuator, the actuator uses buffering, and whenever new data does not arrive, the actuator just reads out the contents, the corresponding contents of the buffer. And these methods work quite well. So that would be using what's called packetized predictive control, where we optimize over open loop sequences and the entire sequence is transmitted. Alternatively, one could also use stochastic model predictive control formulations, where instead of looking at just a, for example, quadratic cost, you may look at the expected value conditioned on current state, parameterize this nicely, optimize over policies, and if you're lucky enough and you optimize cleverly, this could, even when you have constraints, lead to convex optimization problems. Again, somehow you're sending more information that is necessarily needed in order to preempt when issues arise due to non-perfect communications. Okay, simulation study then. Let's suppose we've got a pendulum model, so it's a bit like my arm with a broken, what's it called, elbow, right? It's linearized around the top position. The system input is a torque, it's constrained, so my shoulder is not infinitely strong. We've got n channels with reception probabilities randomly generated from an interval 0.4 to 0.9, so 40% to 90%. We don't know how good the channels are. We want to learn while doing control. We choose a quadratic cost function of this form, where the final state weighting matrix comes from the associated algebraic Riccati equation of all of this. And we send deterministic sequences. Let's see what happens. Well, this is what happens, right? If we use the Thompson sampling, so, okay, x-axis, we've got time, we've got the control regret, which would be then the distance between the stage cost with the controller used and the estimation and the learning algorithm used compared to the optimal one. We've got the control regret over time. Of course, this does not decay, it grows in general, it's a cumulative measure. It exhibits logarithmic scaling, as we can see from these pictures. The blue curve is horizon 1, orange curve is horizon 2, green horizon 3, red is horizon 4. We can see that larger horizons give better performance. This is all using the Thompson sampling. We still have logarithmic scaling, and we're not surprised that larger horizons give better performance. It's something we know from NPC in general. We also know there's diminishing returns. Up to a certain point, we improve performance. After a while, it's maybe not really useful or needed anymore. Now, if you compare this to alternative methods, because there's lots of things one can do instead of Thompson sampling. We could periodically just explore channels, let's say every 70 time steps explore channels, and at other time steps within the period select an apparently best channel. We can use epsilon greedy with a decaying exploration rate that satisfies all these nice conditions. We could use Q-learning as well, where we've got also a decaying learning rate and a reward which is given equal to the success probability. And an artificial, a dummy state that just stays the same. This is just a selection problem. And we can see actually that if we compare the Thompson sampling method to the other methods, Thompson sampling outperforms the decaying epsilon greedy method, it outperforms periodic sampling, and it by far outperforms the Q-learning with a table approach. Because Q-learning, yes, everything's finite, so you can prove it will converge. It's just very slow. because it has to transverse everything all the time in order to learn from the system. And it does not use this whole posterior sampling idea. So, let's summarize then. We studied a remote control scenario where wireless sensors and actuators can choose between a number of channels, and those channels, we have a model, but we don't know the parameters of the models. So we've used bandit algorithms to learn the statistics of the channels, while at the same time do estimation and control. So everything works at the same time. There's no offline learning. And we were able to then establish conditions for stability of the system using these algorithms, as well as quantitative performance bounds in terms of regret, control regret and estimation regret. And provided we can sample from the posterior in an efficient manner, using Thompson sampling could be alternative, really interesting alternatives to epsilon greedy or Q-learning. This is preliminary work. Like this is just hopefully a beginning of other works. So extensions, yes, I've said that the channels are fixed. Well, channels will in general be time varying. Time varying, maybe we know something about how they vary, maybe we don't. So how do we extend this? We may want to look into allocation of multiple channels to multiple dynamic processes. So look into a larger network scenario. We've worked a bit on that using reinforcement learning. We haven't looked into this using Thompson sampling yet. And we may also want to look into state-dependent explorations. Don't explore all the time. Only explore when it is reasonably safe to do so. So, in case you're interested, of course, you can ask questions now. I'm also here, I think, until Saturday, so I'm always happy to have a chat. You can also look at the papers that this is based on, and I would like to thank you for your attendance, and thank my friends Wan Chun and Alex as well, because we worked on this together. Thank you.
So thanks, Danielle, for the nice talk and for staying in time despite the technical problems. The floor is open for questions. Maybe then or Moritz?
Yeah, thank you for a wonderful introduction to this topic. I didn't know Thompson sampling. I just wanted to ask if you would have, like, say, stochastically driven theta. Is there also closed form solutions for some of the distributions that come, or how would you proceed? I mean, it's one of your outlooks, but can you give an idea of how one would treat, let's say, a non-stationary theta?
Okay, so it's a very important point related here to the time-varying channels, right? So the expressions I used here are assuming that the channels are fixed. So theta is given, and then this is the posterior, and this is precise. If there's time-varying theta, we would have an aggregated model with additional states. I'm not sure what one could say about the expressions for the posteriors. We would have to look into more detail. You have got like for example, things like hidden Markov chain problems. One could possibly adapt the type of method used for Thompson sampling here for time-varying things, because instead of going infinitely back for this beta distribution, you may want to truncate how far back you go, which is, where are we? Here. This starts from the beginning until now, right? But you may want to, these end times just refer over a finite window into the past. You may want to incorporate forgetting factors. You may want to let the channel depend upon something else, which could be like an environmental state saying busy, not busy, and incorporate that as well, which then leads to contextual bandits, for example. I don't know. There's probably a lot of literature and a lot of things to look at. So thank you, Moritz.
Okay, further questions?
I think Mariam had a question as well.
Thanks for the clear talk. I just have a question regarding the if you have tried other methods such as upper confidence bound approaches for the banded learning, and how would they compare?
No, we have not. Actually, all the methods we have tried was the ones incorporated in these last pictures, which is Q-learning with a table, so basic Q-learning with epsilon greedy Q-learning with a given learning rate. We looked into decaying epsilon greedy. This is the best, by the way, this is the best we could do with Q-learning with epsilon greedy, and we looked into just periodic sampling. We did not look into upper confidence bounds or X3 algorithms, any of the other algorithms.
Is there any reason, or do you have any idea about how they could perform?
I don't know.
Okay.
The truth is, I don't know. This is preliminary work. So I actually, for today, I chose to talk something that I know very little about. Maybe I know a little bit more than some of you, so I can contribute, but I didn't want to tell a story where I have all the answers already. Yeah?
Thanks a lot. It was very
thank you, Mariam.
clear.
Okay, maybe a question from my side,
Yes.
Daniel. What happens if the channel becomes depending on the state? This is a discussion we had already.
Yeah,
So, you know, the decision you make influences the state, this influences the probability of success of the transmission.
Yes. It's also an important thing, like if the decisions we're making are, for example, on moving a robot, and the robot is a big metal thing that changes the communications, or it changes where it is at the moment, this active probing type problem we have not looked at.
Okay.
Right?
Any ideas?
And it's sort of related, it's a step, I mean, Moritz, you raised one problem, and this is the additional problem, right? It's another thing to look at. So, not much I can say about this.
Okay.
Yeah?
I think with this one, I check the audience again. I think I keep you, or we keep you from the coffee, which is important for staying awake. So thanks again,
Yep.
Danielle.
Thank you.
For the nice talk.